Okay, so 5.8/5.9. We're going to talk about analyzing some graphs of polynomial functions today, and then we're going to talk about, that's Algebra II, graphs. And then we're going to talk about some other functions of polynomial factors too. Zeros, factors, solutions, and intercepts. Okay, so if you have a function where it's like ax to a power plus ax to the next power plus ax to whatever power until you get down to no powers, okay, that's a polynomial function. If it's a polynomial function, the following statements are equivalent, okay? Zeros, when you're looking for zeros, k is a zero of the polynomial function of f. Factors, x minus k is a factor of the polynomial function of f of x, meaning what we've been doing when we have x plus 2 in parentheses and we set equals 0 and you get x equals -2, that's what it's saying right there, factors. Solutions, k is a solution of the polynomial equation f of x equals 0, and x-intercepts, if k is a real number, k is an x-intercept on a graph. All things that we've dealt with and talked about, nothing new. So, if we look at this graph right here, use x-intercepts to graph a polynomial function. What are my x-intercepts? -3 and 2. How many 2's though? 2. Which means does it cross through or does it turn? It turns, okay? So, graph. You can erase that junk that's up there. Okay, so put a dot at -3, yes. Well, yeah, at -3, because that's one of my x-intercepts. Put a dot at 2, correct? Because that's another x-intercept. Okay. Now, we have to talk about what we do, how we graph the rest of this. What would you say we would do to graph the rest of this? Any suggestions? Slope. That's not no line. This is a polynomial function, not a linear equation. No, not rows over 1. It's actually pretty simple. You're going to plug in points on both sides of those dots and in the middle. So, on the side of -3, let's plug in -5 and -4. Okay, if I plug in a -5 to this equation here, okay, if I plug in a -5, you get this. 1/6, you get -5 plus 3, oh, this is off. You get 1/6, -5 plus 3, -5 minus 2 squared, yes? What's -5 plus 3? What's -2? -2. And then what is -5 and -2 together? -7, what's -7 squared? What's 49 times -2? -98? Yes. And then what's -98 times 6? Or divided by 6? Tell you what's up. Oh. I don't know. See if it's in that stack of money that's by me. What's -98 divided by 6? Well, someone does it. I'm not doing it for you. Elle doesn't have to be responsible for the whole class. So 16 2/3. So -16 2/3. So I would graph, this is your turn, -5, -16 2/3. Because I know that you said he said 0.33, is that what you said? It's 1/3, not 2/3. Because I just know that 0.33 repeated is 1/3. Off the top of my head. Let's plug in a -4, okay? So if I plug in a -4, I get 1/6 times -1, right? Times -6 6, what's negative 6 squared?
36.
So then you get negative 36 times 1/6. What's negative 36 divided by 6? Negative 6. So graph negative 4, negative 6. Okay, so now I have 2 points on that side. Now I'm going to graph 2 points in the middle, then I'm going to graph 2 points on the other side so that I know what the figure looks like. Does that make sense? So let's graph, actually I'm going to graph 3 points in the middle. Let's graph negative 1, 0, and positive 1, okay? If I plug in a negative 1, okay, then this becomes 2, this becomes negative 3 squared is 9, and 9 times negative 2 is negative 18, and negative 18 divided by 6 is negative 3. So graph negative 1, negative 3. Okay. That doesn't make sense. Negative 1 should be negative 3. That's because this isn't negative. It's negative 1, positive 3. I'm sorry. I just can't read. Okay, now we're going to plug in a 0. If I plug in a 0, I get 0 plus 3, which is 3. I get 0 minus 2, so negative 2 squared is 4. 4 times 3 is 12. What is 12 divided by 6? 2, so 0, 2. Then I'm going to plug in a 1. So, this stuff tonight is not difficult. It just takes some time and patience. 1 and 3 is 4. 1 and negative 2 is negative 1. Negative 1 squared is 1. So I get 4, and I get 4/6, which is 2/3, yes? So 0 2/3, or 1 2/3, yeah, there you go. Now we're going to plug in 2 numbers on the other side. I'm going to plug in 3 and 5, just to spread it out a little. So if I plug in a 3, you get 6, you get 1, you get that, so you get 3, 1, yes? And is it supposed to turn there? Yes, because it was x minus 2 squared, so it's supposed to turn and not cross through, so that's beautiful, we like that. And then I'm going to plug in a 5. That makes this 8. That makes this 3 squared, which is 9. What's 9 times 8? 72. 72. And 72 divided by 6? So then you get 5/12. And now connect those dots. Thanks for doing that all kindly and everything. So then you get that in type figure. I know, do it with that one. Overshot. Okay. So, all the way up. Do you see how this is working? Is that difficult to do? No. You graph the intercepts first, then you have to graph 2 points on the outside, 2 points on the inside, or if there's 3 intercepts, do 2, like, just make sure you do 2 in between each section so that you can see if it's curving, you know what I mean?
So you did 2 points.
I did 2 on the outside of that negative 3. I did 3 in the middle because I wanted to see it curve, so I did a little closer to see, and then I did 2 on the outside. It's kind of a guess and check game. If you feel like the graph should look a little different or it's not like curving right, then you need to do another point inside there or something. Okay? So that is pretty much the first section of this. The second part is maximum and minimums. On that graph, we have a maximum and we have a minimum. Every time there is a turning point, there is a maximum or a minimum. So, good. That first turning point would be a maximum, okay? The second turning point would be a minimum. So that's what we're looking for. So if they ask how many maximums or minimums are in your graph, you tell them. If they ask what the point is, you're going to eyeball it if it's not perfect because we don't have graphing calculators to press a trace feature and tell us exactly where it's at, okay? So your answers are going to be a little off. It's okay. But that's the easiest part probably is finding local maximums and local minimums, okay? So then, the next part is getting a graph and creating a function off of it, right? The cubic function whose graph is shown. Cubic means what should it end up with? Like x cubed. Okay, I have 3 x-intercepts and I have a y-intercept, yes? Okay, so if I'm writing a function of this, this is 5.9 because we skipped the rest of 5.8 after that maximum minimum thing. So if I'm doing a cubic function, okay, I know that functions always say something like this. Y equals a times whatever, yes? Okay, I have 3 intercepts right now, so tell me what those parentheses would say. What's the first one gonna say? X plus 4. What's the second one gonna say? X minus 1 and x minus 3. Okay, now, we need to figure out what that a is so that we can solve this cubic function all the way. That's why they gave us a y-intercept, or another point on the graph. It doesn't matter where it's at. If they give you another point, I can solve this. Because I'm going to take that 0, -6, and I'm going to plug it in for x and y to solve for a. So my y is -6. My x in this case is 0. So this is how I'm going to solve. So I have 4, I have -1, I have -3. What's 4 times -1? And -4 times -3 is positive 12, yes? Divide by 12 and a equals what? -1/2. Now my equation is y equals -1/2 x plus 4 x minus 1, x minus 3. What do you think I have to do from there? Is that in cubic function form? Actually, they're not going to make you factor it out. They're only going to make you write it that way. Because it's in intercept form. So I can just leave that. This is my equation. Okay, not too difficult. You don't have to do a lot of math there. You just have to know what you're looking for. Okay. And then the next thing we're going to talk about is some pattern stuff. Something called finite differences. Okay? So we found a function given its graph. Okay? Functions can also be written from a set of data using finite differences. So this is where we're given a graph. If we're given data, we can still create an equation. Okay? When the x values in the data are set equally spaced, meaning there is a pattern between them, okay? The differences of consecutive y values are called finite differences. For example, finite differences for the function f of x equals x squared are shown. If I plug a 1 into here, okay, I get a 1 out, correct? That's what this is telling me. If I plug a 1 in for x, I get a 1 out. If you plug a 2 in, you get a 4 out, okay? If I plug a 3 into x, I get a 9 out. If I plug a 4 into x, I get a 16 out. If you plug a 5 in, what would you get out? 25. The pattern is this. The difference between these two numbers, from my second answer to my first answer, is 3. The difference between 9 and 4 is 5. 16 and 9 is 7. What's the difference between 25 and 16? 9. So what is the pattern that's going on there? Odds. They're counting by 2s with odds, yes? The differences. The finite pattern is that the difference is like that. You're going to have to start recognizing patterns. Okay? The finite differences are called first order differences. Okay? You can calculate higher order differences with what we're going to do with this. Okay? So, the first 5 triangular numbers are shown below. A formula for the nth triangular number, meaning, let's say I want to know what the 99th term is. That would be the nth term in this case. Okay? The formula for that is 1/2 times n squared plus n. Show that this function has constant second order differences. So what is this graph telling me? If I plug a 1 in, I get a, if I plug a 2 in, I get a 3, 6, 4, 10, 5, 15. Okay? So what is the pattern that is going on in between there? Here's how we do this. we take those numbers, our outputs, okay, we say f of 1, 1, f of 2, 3, f of 3, 6, right? F of 4 is 10, and f of 5 is 15. Then we find the pattern. We subtract these. What's 3 minus 1? 2. Okay. What's the difference between 6 and 3? 3. Difference between 10 and 6. Difference between 10 and 15. Okay. Do you see how that now is taking us down to 2, 3, 4, 5? What's the difference between 2 and 3? 3 and 4? 4 and 5. When I get to all ones, I need to stop. Okay? That tells me something. This tells me what type of function this is. Okay? So if you see, the first order differences, okay, are that first row that we get. 2, 3, 4, 6. Those are the first order differences, the difference between the first rows. Okay? The second line is called second order differences, and we got all ones. Okay? Because I subtracted them again, the second order of differences. Each second order difference is 1. So the second order differences are constant. Okay? That means that this is a squared function because I have 2 levels. So I have a square, which makes sense because I have a square in my equation they gave me. Okay? So, properties of finite differences. If a polynomial function, f of x, has degree n, the nth order difference of the function values for equally spaced x values are non-zero and constant. So they can't be zero numbers and they have to be constant numbers. Okay? Conversely, if the nth order differences of equally spaced data are non-zero and constant, then the data can be represented by a polynomial function of degree n. Okay, look at this one. The first 7 triangular pyramidal numbers are shown below. Find a polynomial function that gives the nth triangular pyramid number, meaning we've got to come up with the equation of this. Okay, so we need to set it up and look for patterns to see what's going on. So, the first thing we have is f of 1 would yield me 1. What does f of 2 give me? 4. What's 3 give me? What's 4 give me? 21.
20.
What does 5 give me?
35.
And what does it go up to? 7. What does 6 give me?
56.
And what does 7 give me?
84.
Okay. So we need to see what type of pattern is happening here. Okay? So by doing that, we're going to use the finite differences, which means we're just subtracting all these things. What's 4 minus 1? What's 10 minus 4? 20 minus 10? 35 minus 20? And 56 minus 35? You forgot? Is that what you said? 21. 21. Okay. And what is 84 minus 56? Okay. Those aren't all ones, so we have to keep going. 6 minus 3. 10 minus 6. 15 minus 10. 21 minus 15. And 28 minus 21 is 7. Those aren't all ones, so we have to keep going. 3 minus 4, or 4 minus 3. 5 minus 4. 6 minus 5. And 7 minus 6 gives me ones. Okay. So now I have something where I can see what's going on here. Okay? Now you have to do some math here. This is where it gets real fun. Okay? So we've got to look at the patterns overall. In this, because the third order differences are constant, okay, third order, this is first order, second order, third order, because the third order difference are constant, we can stop, okay? You know that the numbers can be represented by a cubic function, okay? This gives me cubic because we did it 3 times. Cubic functions are represented by a, or y equals a x cubed plus b x squared plus cx plus d. Okay? So now we're gonna have to create some formulas off of the numbers that we're given. Okay? Ax cubed, bx squared, cx plus d. By substituting the first four triangular pyramidal numbers into the function, you obtain a system of four linear equations. Okay, so we're going to substitute in these first four numbers for x. Okay, so we're going to go like this. We're going to say y equals, okay, or we're going to sub it in not for x but for the x part. We're going to say a times 1 cubed plus b times 1 squared plus c times 1 plus 1. No, plus d. Right? And they should be set equal to whatever I get out of when I plug 1 in. I get a 1 out. Okay? The reason I need to do four equations is because I have four sets of data here. Okay? Now for the second one, I get 4 out, and I plug it in, and I say a2 cubed plus b2 squared plus c2 plus d. Okay? See how d always stays constant? It's because we're going to do substitution and elimination, and it will eliminate itself. Third row is 10 equals a3 cubed plus b3 squared plus c plus 3 plus d. Then the fourth row is 20 equals a4 cubed plus b4 squared plus c4 plus d. Okay? Now what we're going to do is we're going to simplify all those equations. This equation right here simplifies to 1 equals a plus b plus c plus d, yes? Okay. A plus b plus c plus d. Okay. This equation simplifies to 4 equals, what's 2 cubed? 8. 8a plus 4b plus 2c plus d. This equation simplifies to 10 equals, 3 cubed is 27. 27a plus 9b plus 3c plus d. Okay? And then the last one transfers to 20 equals 4 cubed, 16, 64. 64a plus 16b plus 4c plus d. Okay? Transfers to that. This is how far I'm having you take everything. Only to that. Because here's the deal. To solve the rest of this, we would have to use a matrix. Problem is, this would be a 4 by 4 matrix. We don't want to do a 4 by 4 matrix. And we don't have graphing calculators to do 4 by 4 matrices. So all you're simply doing for me is getting them into the equation form, simplified. Got it? Okay? If you can go that far, I know you can do the rest. Once I give you a graphing calculator, I can teach you that next year. Okay? Not a problem at all. So if you can do this, tell me it's a cubic function and get it into those simplified forms, that's as far as we need to go. Okay? Like I said, we modify a lot today. So that's what we're looking at for that. I don't need a full answer. So on your homework, this is going to be the problem. On your homework, it's going to ask you to give the full equation, and that's what's going to be the answer in the back of the book. You can only do that when it is squared, because if it is squared, we're going to do substitution and elimination from there. When it's 4 like that, I'm not making you do substitution and elimination, okay? When it's squared, you'll have 3 equations instead of 4, and you know how to do substitution and elimination with 3 equations. Okay? So when it comes to 3 equations, that's what I need you to solve. When it doesn't, then just leave it, and your answer's not gonna match the back of the book. We'll go over it tomorrow, don't stress. Okay? That is what we're looking at tonight. Kind of a little tidbit from each